Hi, my name is Andrew McLaren. Today we're going to go over cell potentials in AP chemistry. We're going to be doing that by going over what you really need to know. There's a ton of standards that you can look at, but we're really going to be doing more of like a big picture kind of lecture style overview, going in depth about what these things really mean in more like understandable terms. So we'll look at those a little bit more in depth, and then we're going to look at a couple different example problems from the AP exam just to clarify what this really means, because I think a lot of AP chemistry teachers are a little bit off target in terms of what they're teaching and what is actually on the exam, or they may be teaching stuff that goes a little bit beyond the exam, although most college classes give you easier things. So I know a lot of students get worried that they're going to have to draw out a battery, but this is really going to be labeling some sort of part or saying what reaction happens at a part. So this is going to be a lot simpler than what most people think. So it's going to be either at the cathode or the anode. And so you need to know what reaction is going to take place at the cathode or the anode, and what you're going to be determining to be the cathode and anode is going to depend on if you're in like a galvanic cell versus like an electrolytic cell. So it's important to know that there's these two opposite things and being able to recognize which words go with what. So if we're talking about something that's galvanic or voltaic, that is going to be thermodynamically favored. And that is the word that you really need to like key into, is the thermodynamically favored. Because that's what I've seen them use in the AP exam. They don't really use galvanic and voltaic or electrolytic or electrochemical. Those are terms that you're going to see online, but on the exam, they're going to either like tell you that it is that or say something about the thermodynamic favorability. So to summarize that, what we want to do is we want to think about spontaneous versus non-spontaneous. So if we're talking about spontaneous, that means it goes forward on its own. And this does not go forward on its own. So this needs energy to go forward. And by go forward, I mean make more product. So that's the big picture. Are we making more product when we're considering this reaction, or does it need energy to do that? Will it do it on its own, or do you need to power it? So if we're talking about spontaneous, this is what I would think of as something that's thermodynamically favorable. Versus the non-spontaneous, which is going to be thermodynamically unfavorable, right? So we've got the spontaneous versus the non-spontaneous. I'll just do a little bit of cutting the corners here a little bit. So this is unfavorable, where this is favorable. And if you know that, then that's really, really useful in terms of like figuring out what we're talking about. But really what you're going to need to then relate that to is what that means in terms of the voltage. We'll get to that. That's more in like the 9.8. But there is something that I want to also point out here, and that is that you need to know that the oxidation occurs at the anode and the reduction occurs at the cathode. So this is sometimes remembered with red cat on an ox, and I actually had some images of like AI generated things and red cats on an ox. And so I would like to show you that to help you remember that saying just a little bit better, because it's like you can imagine like some sort of red kitty cat, right? Sitting on some sort of ox. So there's some sort of horned creature here. And so we've got our big bulky ox with a red cat on it. So that might be enough for you, but we'll get some AI images to make this really clear. You do need to know where the oxidation is and where the reduction is, that's probably going to be where you need to determine what reaction is going on at the cathode and anode. So that's really like, is oxidation happening here? Okay, so what is losing electrons? So you're going to need to use that in conjunction probably with Leo says Gur. And I have a whole video on Leo says Gur. That should be something more from like reduction half reactions, which you should already have down at this point. So here we have some images that will help you with a red cat on an ox. This one's okay, but it's a very red ox, so it's kind of weird. But AI was having a hard time getting a cat on an ox. This one looks like they're almost like sharing like 3 legs almost. It was a little bit weird, some of the AI generated that came up, but hopefully the weirdness helps you remember that a red cat sits on an ox, and that's like reduction goes with the cathode. And so yeah, we're basically saying reduction is with the cathode and the oxidation is with the anode. So that's the red cat anox trick to help you remember that. So that's kind of important, but the big picture for me is that the thermodynamically favorable, this is going to be connected to positive amounts of volts. That is pretty important to recognize that we're going to have positive voltage here when you have something that's thermodynamically favored, and the opposite is true when you've got the thermodynamically unfavored. That should be a negative voltage when we're talking about these energy potentials. So that's a very important thing that is going to be connected, where you need to recognize what thermodynamically favorable means in terms of it being spontaneous or not. And then you need to connect that in terms of the voltage, which is a bit weird because a lot of things are negative that are spontaneous in this AP chemistry course. So it's important to just really clarify that a positive voltage is spontaneous. And I actually, I'm going to kind of jump down to this formula here, because this helps me remember this a little bit. So this equation, you can see where we've got this change in G, negative N, F, and then this electrical potential of the cell. So this is of the reaction, and this is going to be a nice way of remembering the positive-negative relationship between these things. So you can imagine here where if I'm plugging in something positive for this, then the value of this overall thing is going to be negative, and you're going to get a negative change in G. Whereas if I'm plugging in a negative here, then that is a negative times another negative, so the value of the whole thing becomes positive, and you get a positive Gibbs free energy. So if you know that like Gibbs free energy should be negative, not spontaneous, then you can use this formula to reinforce that a positive voltage should be spontaneous. If you get confused about how the signs relate, use these formulas to help you relate it. This other standard that's in the middle here, so I've already covered these two. This guy is talking about like combining the two voltages, and the fact that you don't need to multiply by the number of like things that you need to multiply them to combine the two half reactions. So this is like their intrinsic properties. We'll go over that a little bit more in terms of like an example problem. But that is where you sometimes see this formula where they have the energy of the cell, and that's the energy reduction minus the energy of oxidation. And I really don't like this formula because I really think it is more appropriate to think about combining these two electrical potentials. But this is now the negative of what was the reduction of the thing that isn't actually being reduced. So this can be a little bit confusing. We'll go over that more with an example problem, and I'll kind of try and tie that into this other stuff that we're talking about. So there's a whole lot going on there, but we've only really talked about standard conditions. And this is a little bit weird because we talk about cell potentials under non-standard conditions, but we don't do Gibbs free energy in non-standard conditions for AP Chem, which can cause, to say the least, quite a bit of confusion. So we need to really talk about what is standard, like define that. And they've got it defined here, but it's a very small point. Like Q should be 1 for a standard condition. So if we're talking about any sort of equilibrium, the Q of equal to 1 is kind of right in the middle in terms of the values that you could be getting. Because remember, Q, this is a ratio of products over reactants. And it could be for various formulas. It could be like A up to the second power, B up to the first power, over C up to the third power. Like there's all these things that could be going on there. But if you have concentrations of 1 molar for everything, Q should be 1, no matter what. Those exponents doesn't really matter when you've just got 1 molar up to the second power times 1 molar all over 1 molar up to the third power. That still gives you a Q value of 1. So this is the standard starting point. And it's assumed to be 1. So now this gets to, well, how can we think about this in terms of relating to spontaneous, non-spontaneous, and then non-standard conditions, and if it is spontaneous or not. So if something is what we would say like spontaneous under standard conditions or non-spontaneous under standard conditions, then you get this dot, this little dot. That means we're talking about standard, which is then thinking about like, well, Q is 1. So if something is going forward, what does that mean? That means that the K is bigger than the Q, meaning that we should want more products to be formed. So you can think about like K equilibrium for like one thing that's thermodynamically favorable, where the K is over here. So it is going to readily move over and it makes more products. So it needs to go from here to there. So that's going to correspond to, like, that difference right there corresponds to how much energy or voltage it needs to use to, or give off to go from here to there. So if you can have a very, very big Q, so if you had like another Q that's even bigger out here, like K equilibrium 2, if this is bigger, then it's got further to go, so it's going to release more energy and have higher voltage. So the further it goes, the bigger that energy released. And you can imagine that this is the same sort of deal when if we're talking about K equilibrium of something that is non-spontaneous, it doesn't go forward on its own. So it would maybe spontaneously go backwards, but this is kind of weird because it is normally wanting to go backwards here. It's like, okay, this would release energy if it was able to go backwards, but it requires energy to now go forward. And this is the E required to make it go forward. And we'll talk a little bit more about that in just a minute, but if you've got something that has an even smaller K equilibrium, then it's going to require even more energy to get that to this Q value of 1. So you can see that there's this relationship between this K equilibrium and these standard conditions. And in addition to all of that, you can start not at standard conditions. So what if you're starting right here? So what if Q does not equal 1? So what if Q is kind of big? So now there's a different amount of energy that's released and a different amount of voltage that is required. So that's the main idea. You don't really need to do too much math per se with this, but they do have a formula here where you can imagine that there's the standard voltage, which might be negative, and then there's this component which is either making it more negative or less negative, depending on how you want to think about it. So the formulas that come into play that help me think about this is the Gibbs free energy. There's a standard Gibbs free energy, and then I think it's minus RT ln Q. I would need to double check that. But then we've got this other one where we've got the electrical potential, which is related to the standard electrical potential minus the RT NF over ln Q. I'm pretty sure that those two are correct. So you can, let's just kind of make some numbers up just to get like that idea across. So if this was a negative 10, okay, I knew there was a small error in here. This should be a positive sign right here. So if you've got a Q that's bigger than 1, then it's going to affect this. So you could imagine like the standard condition. What if Q is equal to 1? Well, this whole part just is gone and you've got the standard Gibbs free energy. But what if that Q is actually bigger? So it's like it's greater than 1. So that means that this whole thing ends up kind of bringing up this Gibbs free energy, so it's not quite as negative. So it's not giving off quite as much energy. So there's a different amount of energy. There's actually less E released when you have this Q that's bigger than 1 when we're talking about spontaneous. So this could maybe be making it go up 5. So instead of being negative 10, this might be a value of like negative 5 kilojoules or something like that. So it doesn't have to go as far if Q is bigger than 1, so it's not going to release as much energy. That's the really big picture on this. And the same sort of thing happens with the electrical potentials. And although this formula isn't on the AP exam, there are questions relating to this conceptually. So you'll see that soon. So if we're talking about the spontaneous thing here, this might be like a positive number. This might be like, let's just say a positive 1 volts or whatever. And then this, maybe this is now minus 0.5, because if this is big, then that means this whole value is positive within the ln, which means with the minus, you're going to have to end up subtracting that. So you end up with a voltage that's not quite as positive here. So it's less of a positive V when we're talking about this in this situation. Now you can imagine the same sort of stuff is going to happen where if we're talking about a positive 10 volts, so if you're maybe going from here now down to, like considering going from this to the non-spontaneous, so it's like this thing needs a certain amount of energy to go forward. And this now Q is making it need even more energy to go that much more further forward. So it might be like plus 10 and a plus 5 resulting in plus 15. So that there's more energy required to make this go forward a certain amount. Now, this is where I like to think about these things kind of canceling. So if change in G is 0 or the change in this electrical energy is 0, that means that this is these two parts are canceling out, right? So it's essentially meaning that K is equal to Q in both of these cases right here. So if we're thinking about this where we're like, okay, well, if I cancel out how much this reaction normally wants to go forward by making it harder to go forward, then it's just not going to go forward that certain amount. And that's where I like to think about these voltages. If you have something where it's like, oh, you've got minus 1 volts. What that's saying is that you need to supply that many volts for it to go forward. So if this ends up canceling out and being more like plus 1.1 in terms of the values here, then this is spontaneous and it goes forward. So the values that you're getting when you're talking about things that are electrolytic or requiring some energy, that's how much you need to supply to start getting it to go forward, to get this to actually want to go and form product. To drive this home, there is another equation that you're probably seeing on your formula sheets where you've got the Gibbs free energy and you've got minus ln the K, and then I think there's R and T and a minus RT out front. So this right here you can plug in right there and you can see that it's going to end up canceling out. So one's a minus and one is a positive. And so if K is equal to Q, they end up canceling out. And on that number line, you can think of that as like, oh, I'm starting at K equilibrium here, and this is Q, so like it doesn't need to go forward. So for Faraday's law, this is very common where they will give you a current and they will give you some time and they want mass. They want some sort of mass deposited. And there's going to be some sort of dimensional analysis where you're kind of canceling things out and you're going to be working with time and you're going to be using the current because that will be some charge over some time to then ultimately relate that charge to like electrons and the then the atoms that are being deposited, and then like you're going to use molar mass to get the grams. So there's going to be some sort of dimensional analysis, and there's usually some sort of mass that's being formed. But you need to be careful because this question can be almost a trick question. We'll go over that in the example questions. Like the one from last year was kind of like this, but you need to be careful with the wording because it's a little bit different. So for our first example problem, this is the most recent one from 2013. And you can see that they've given you a couple different half reactions. And they've also told you they want the thing that's the most thermodynamically favorable. So our goal is to get a positive voltage. That is going to be ideal. That's kind of what we want to do. So I'm looking at these things that are present. I'm trying to think like, how can I make a positive voltage from some of them being negative? And there isn't that 0.15 is kind of positive, but it's not that positive. So this gets at that whole equation where there's the energy of the cell relating to the energy of the reduction minus the energy of oxidation, but it really should be plus the energy of oxidation. This is oftentimes not even given as a formula to students. They're just kind of, they need to know how to work through this. But what we can see is that there is, like, if I could flip that, that would be great. So if I'm thinking about the opposite reaction, like now, this would be a positive 1.28 if we're talking about zinc solid now going to form like the zinc oxide, that reaction. So it's, you flip the reaction, you flip the voltage. So we really want to work with the 1.28 as a positive value. And that's going to be our thing that's being actually oxidized. So you're really adding a positive 1.28 to a positive 0.15. Because this is just given as is, you don't need to flip the sign. This is where they sometimes in this, they'll say that you're subtracting the minus 1.28, but I think that's a little bit weird because it really is the voltage potential of the opposite process. So if something is not spontaneous going one way, it is spontaneous going the other way. So this is adding to the spontaneity if we're able to flip the directions. So we really want to use these two half reactions. So we're looking at this guy right here, and we're looking at that guy right there. But we want to expand this out just a little bit more and actually write them out correctly. So if we're doing a positive 1.28, we've got the zinc solid here. And that's water. The nice thing is that these both have 2 electrons in them, so they'll cancel out kind of nicely. I've got the zinc oxide that's that solid. And that's actually going to be actually I'm messing this up. So if I flip my sides, I now need the water over here with the zinc oxide and the 2 electrons, and then the zinc that's solid is going to be with the 2 OHs, the minus. So now the reactants that were on one side are now the products because we've flipped the reaction. So we've got that one flipped. Then the other one is kind of easier because you just write it as is. So we've got some water, H2O, 2 electrons, and that will form the magnesium 2 oxygen 3 solid. And we've got one more thing here, plus 2OH minus. There's a couple things that get canceled out between the two. You can see that our 2 electrons, those get canceled out. Looks like the 2 OHs are also getting canceled out. And the water looks like that also cancels out. So it leaves us with the zinc solid plus the 2 manganese O2 solid reacting to form zinc oxide plus Mn2O3. And it's always good to just double check that things actually are balanced when you do these things, because it's an easy thing to mess up. So I'm seeing 1 and 1 on those. I'm seeing 2 of these on both sides, and I'm seeing 4 oxygens on both sides. So this does look like it's balanced correctly, like so. So that would be what you do for this first one. And then the E of the cell, we've actually already kind of thought about that. So it's the 0.15 plus the 1.28. So 0.43, I believe, for the volts there. That should be a positive, because that is going spontaneous, and that is as spontaneous as you can make it. You could imagine, you could maybe try flipping the 0.76, but that's gonna not be as positive of a result. So then we've got this other formula with the Gibbs free energy. We've got Gibbs free energy is equal to, I believe it's the negative NF, and then E, the cell potential. So this is fairly straightforward. You just need to use your constants. So we've got the cell potential right there, 1.43 volts. Now we are going to need to account for the number of electrons, though, that are being transferred. There's 2 electrons that were being transferred here. So there's N of 2 right here. And then the Faraday's constant, I would need to look that one up. So just give me a second. So to get this part, we're going to need to use our Coulomb value per mole of electrons. So we've got that coming into play here. That's the 485 coulombs per mole of electrons. Because there's 2 moles E per reaction, basically, that you can think of the moles canceling out. And then this is volts. And remember, 1 volt here is equal to joules per coulomb. So instead of writing this as volts, I'm going to write this as joules per coulomb. And you can start to see how like the coulombs cancel out, the moles E cancel out as well. And this should then leave us with something that's just in the value of joules, but they want it in kilojoules. So you would do this math. Let's just go ahead and do that. 96485 times that 2 times 1.43. Okay. That's joules per reaction. And so if you want to do that as kilojoules, you just then are going to convert joules to kilojoules. 1 kilojoule, there's 1,000 joules. So you need to make this 1,000 times smaller. So this should be 275.947 kilojoules per reaction. And then we just do our sig figs, which I believe was, 3 sig figs on that 1.47. 276 kilojoules per reaction. So we've got that answer for our third part, and then we can answer this fourth question. Now this is a little bit tricky because it almost seems like Faraday's law, but it isn't actually. So this seems like it's like, hey, how much mass is going to get deposited over time? And there is going to be mass deposited over time. I believe that We're going to be making the manganese oxide, so that manganese oxide should be getting a little bit heavier, that thing right there. But we're going to actually have the zinc case is going to start oxidizing, so that should get a little bit heavier. So some parts might get heavier, some other parts might get lighter, but the whole battery should be the same because electrons have moved, but no new mass. So this battery still has the same total mass, so it seems like it might be a Faraday's constant problem, but it actually isn't. So this is a trick question. This is totally relating though to that 9.10 standard. You just need to be careful on the wording on these things. So the battery itself, the whole system isn't changing, but some components are totally getting heavier. And you could add that in, but you don't really need that in. So this question is from 2022, and it's kind of a cell potential thing. It doesn't really look like a battery that you're used to thinking like there's no salt bridge or whatnot, but we do have a reaction here, and we do have the half reactions that are corresponding to what we've got going on as well up above. The nice thing is they've even shown you that the aluminum there's less aluminum. So you can kind of see that there is aluminum turning into this. So I think we're going to need to flip this guy just by seeing that the aluminum, there's less of this. And so we're not forming more of it. If you were to run electricity through this, you might be able to form some more of it, but that's not what we're looking at right here. So we're going to need to flip this second potential. And so we're getting the 0.80 and then plus 1.66 volts. And so what would that be? 2.46 volts in the positive direction. So this other reaction can make it more spontaneous if we're having the opposite reaction, because it wouldn't go forward with the reduction. It absolutely will go forward with its oxidation. So this is that idea of you're really adding the E reduction plus the E oxidation, but the E oxidation is the minus of its reduction potential. So these end up adding up where this is helping out with that 0.8. And that seems reasonable to me. Now, one of these has to be flipped. If we were to flip the 0.8, we'd have a negative voltage. So that would not be favorable. So if we're thinking about this problem, and it's spontaneously happening, because this is talking about spontaneous. So this is kind of like what you're thinking of, like voltaic, where we want a positive voltage. So the standard free energy right here, so if we're doing the change in G, and that's minus NF, and then the energy cell potential. So because we know that this was a positive cell potential, the standard potential for this should be minus. So if we're saying that like Q is 1, this thing is like, okay, go ahead and go forward. I will spontaneously do this. So a negative thing is spontaneous. And you can talk about that being energy being released, and you can talk about enthalpy and entropy kind of coming together. So there's a net release of energy into the universe, or in the total system of the universe, having the system and the surroundings. So that you can justify with that formula. You can also talk about conceptually. But when the reaction stops proceeding, that means that K is equal to Q. And this is where the Gibbs free energy is 0. You might have this being like the standard Gibbs free energy was negative, but now the Q component is canceling it out. So whatever this value was, maybe this was negative 10 kilojoules. This is a positive 10 kilojoules, and they would cancel out appropriately. So I think that this one's probably the most tricky of the system, because it's not so direct in terms of the information given to you, and you have to do a little bit of this Faraday's law calculation at the end there. So there is some mass that's being deposited at the cathode. So this is actually kind of a clue that the magnesium right here is being deposited at the cathode, because that kind of tells you what's going on here. And they're also saying that there is a voltage that needs to be applied. So I'm thinking that this is like electrolytic or unfavorable, which is, in other words, saying we want a negative voltage. So if we're thinking about this reaction, you need to think about what's going to result in a negative. And that would be if we were to flip this one. So it looks like we're having the magnesium, which is going a certain way, and the chlorine going another way. So for this problem, probably the easiest way to do this is to actually think about it if it was a positive voltage and the voltaic, and just kind of contrast that with the electrolytic. That's how my brain saw this problem. So if I was trying to get a positive voltage, I was seeing a certain reaction where I wanted the magnesium to actually flip. So is the magnesium giving off 2 electrons, and that would be like a positive 2.37 voltage. And the chlorine 2 plus 2 electrons would stay the same if we're thinking about it as a voltaic being ideal, which is not actually the case. So we'll come back to the electrolytic, but I like to kind of contrast the two in my brain. So if I were to have these two reactions written like so, that would be spontaneous, and I'd get like a positive number here. But what we really have is this magnesium. It looks like it's taking in 2 electrons, and the chlorine is actually the thing that's getting flipped here. So we've got the chlorine minus 2 minus, and that is going to then Cl2 plus the 2 electrons. So it looks like this is really what we have in the problem. So we'll need to refer to this, but it helps me to kind of contrast that. So this would have the negative 2.37 volts and now a negative 1.36 volts here, and you can add those up and you get a negative number. So let's actually see what our positive or negative voltage would be. So you can say that this would be 3.73 positive or 3.73 negative, depending on if we're having it being a voltaic versus an electrolytic setup. So this would be going spontaneous one way. We actually need to supply energy to get it going the other way. So we're supplying exact opposite amounts of what it wants to go to get it to go the other way, or a bit more is how I like to think about that. So we can see that there are electrons here that are adding on here. So we're forming more. If I'm thinking about this problem, it looks like there's electrons that are going and attaching to the magnesium. So I'm seeing electrons here traveling this way, which is what we have. Though if we were thinking about voltaically, it would be going the other way. So the electrons are going this way now because we've applied some sort of power. So electrons, the thing that we need to draw would be what we've got in red, because that was the electrolytic. And it looks like 2 volts is not enough. So if we're thinking about that Nernst equation, there was that standard potential, and then there's the minus the RT over NF ln Q thing going on over there. So basically they're saying, okay, this is a negative. Actually, no, hold on. They're not changing the Q's here. This is where they're saying, is this enough? And we need 3.73 volts to get change in G to be 0. So 2 volts is not enough. Um, if we could get the volts to be positive, the reaction will occur. Reaction will occur forwards. So then we've got this idea where it's like, okay, we've got some sort of mass now of magnesium, and this is that Faraday's law. So we've got the 2.00 grams of magnesium, and we're going to then need to relate that to the time that would be in seconds. So you're going to use your molar mass of magnesium. And then once we have that, the number of moles, then you're going to say, okay, if I have a certain number of magnesiums, how many electrons are going to be deposited? So for every mole of magnesium, how many moles of electrons are there? And I think we said there was 2 for every one of these. And electrons have a certain amount of charge. So electrons right here, if you had like a mole of electrons, that's going to correspond to a certain number of coulombs. And if we're thinking about the amperes, that's kind of what we're, like an amp is related to coulombs. So like that's got to be amperes, that's got to be coulombs over time. So if we're thinking about the C here, then we can relate that to the time through this amperes. That 5 amps is 5.00 coulombs per second. So then we can take the coulombs here, or the rate of the amperes coulombs every second, and then we just multiply across once we have the number of coulombs in one electron and the molar mass of magnesium. And I believe we had on that last one of these last problems, we had the formula sheet that was relevant for this. If we're looking back here, this should have everything that we need on it. And it even gives current there. And showing that as Q over T, and Q should be in coulombs. This is actually Q, the charge. And look, they're even showing you that Q is coulombs right there. Coulombs and amperes. So that should help us out. And then we've got the number of coulombs per mole of electrons. So we just kind of plug those in. That's 9.65 per one of these. And we need the molar mass of magnesium. So just that. $24.35. And you'll end up plugging this into the calculator, and we should be able to get a number. So we'll get 2 divided by that 24.305 by 2. Pardon the cat. That's 845. Just double checking. No, it's 485. 485. Do that times that, and then divide by 5. We should get that now as seconds. 3,000, what is it? 175, but we are going to then end up limiting it to 3 sig figs. So I'm seeing that as 300 or 3,100 and what's that? 80 seconds now. I really like this example problem because I've seen a lot of chemistry teachers do some really weird stuff with this, where they're trying to get students to predict what things are going to react with what. I think that came from this problem which is much, much, much simpler than what I've seen teachers giving their students, where they have to work with water, which is kind of weird because its potentials are based on acidic and basic conditions with 1 mole of H plus and 1 mole of OH. So those don't actually apply. So we're using non-standard conditions. It's very complicated. This problem is super doable compared to what I've seen in that context. And I want to show you how I'd go through it. It's not that bad. So the main thing here is that thermodynamically favorable. So I want a positive voltage, and I want it to be as positive as possible if this is going to happen spontaneously. So we want something that's going to make this Br2. So I know that I'm going to need to flip this reaction. So I know I'm going to have 2 Br minus forming Br2 plus 2 electrons there. And its cell potential is now negative 1.07. Because it's the opposite process. Now instead of happening and giving off that much energy, it needs that much energy to go backwards. So the question is, we need something that will, when you combine it, will be positive. And that should disqualify this 0.53. Because that, if the other thing is now the oxidation, we need something that's being reduced. So yeah, you need to keep the signs on these both being positive, essentially, because you're not flipping either of them. So then we're left with just the positive 1.36. And so that corresponds with this chlorine going through reduction. And you can see that one is giving off electrons, the other one is accepting them. And this would result in a positive value of what is that? I've been doing this video for a while now. My brain's starting to to fail me. Okay, so we got a positive 0.29 volts. That should be spontaneous. So that just kind of comes from the definition of a spontaneous cell. Corresponds to a positive voltage. And that is all you really need to do. So it's not that complicated. You're just trying to figure out which ones are going to actually give you a positive voltage for something being spontaneously going forward. So you can imagine that they might say, well, and a similar thing, well, what if it is a thermodynamically unfavorable thing and you need to make a negative voltage as well? So it would be a similar sort of problem, but this is very manageable. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there. And we can schedule hourly appointments. And I've got a few other things on here, like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.